Fluid power. Moving fluids from one place to another with pipes and pumps, or using fluids to move a mechanical device, like the actuators on these robots, or hydraulic cylinders on heavy equipment. Power in a fluid system is similar to power in a mechanical system, the rate of doing work. Only instead of how fast or how slow we do the work of moving an object, fluid power is how slow or how fast we do the work of moving a fluid. We've seen that sometimes fluid work is done when pressure moves a volume of liquid or gas. We've seen that fluid work is done when there's a pressure difference, or delta P. To turn that work into power, we simply put it over time. The pump in this tanker truck has to do the work of lifting fuel up to the tanks in the wings of the aircraft. The pump is overcoming a pressure difference between the tank on the truck and the tanks in the wings. The rate of doing that work is the power of the pump. The same is true for the pump that fills this water tower. It takes more than an hour to do the work of raising the water up and filling the tank. During the launch of the space shuttle, the entire contents of that tank are emptied in a matter of minutes to provide cooling for the launch pad. Gravity does the same amount of work as the pump, but it does it much faster, so there's more fluid power on the way down than there was on the way up. We have also seen the second way of doing fluid work, when a constant pressure displaces a volume of fluid, such as a piston pump. To turn that work into power, we divide it by time, or measure how quickly or slowly the piston does the work of displacing the fluid in the system. Delta V. These two ways of measuring fluid power are units of work over units of time. Like mechanical power, we can see a rate hidden within the general formula for fluid power. The general formula for power is work over time. In a fluid system, work is pressure difference times volume. Pressure acts like force in the fluid system and causes the fluid to move. But volume over time is a fluid rate. So we can also measure fluid power as pressure times flow rate, or generally, force times rate. Either way, you get the same answers. It was fluid power in the form of steam that enabled James Watt to operate his engine. Although most steam engines are gone today, steam power is still behind some of our most powerful equipment, like these steam turbines at a generating station. Very often, fluid power is used to control mechanical power. Ed Larson assembles very large engines. The power of the engine starts with the fluids that enter the cylinders. In engineering lingo, a cylinder is a jug.
This is a 16-cylinder marine engine. It runs about 115 horsepower a jug, about 1,600 horsepower. We're going to talk just a little bit about how fluid power, we turn fluid power into mechanical power and into the rotational power of the crankshaft. These gauges tell the conditions of the different fluid power components we have on this engine. One is fuel pressure, jacket water temperature, jacket cooling water. We have engine oil pressure that lubricates the engine. Right here, under this valve cover, is where the power for this engine starts. We have a fuel coming in these manifolds to a unit injector. As the piston comes up, this is how we get our power. The injector sprays atomized diesel fuel into the cylinder, and it ignites under the temperature of compression, driving the piston down in the power stroke, down in the cylinder of this engine. This is the piston for this engine over here. The amount of power this engine produces is related to three things. The volume, or the size of the piston we have in the cylinder. The rate, or the RPM. This engine you just seen runs about 1800 RPM. We can run it as little as 1000 RPM. Or we can change the pressure. These engines are designed to run about maximum pressure, so we can't increase the pressure to effectively increase horsepower. So what we do is go to a larger engine with a larger piston, and this gives us more volume in the cylinder and gives us more power. This piston to this piston runs about 115 horsepower a jug. The engine that this piston goes in runs about 300 horsepower a jug. The reason is we have more volume and more fuel-air mixture driving the piston down. But we can do it this way without increasing effective compression ratios.
Great.
After this gas drives the piston down into the cylinder, we collect the exhaust gas through the exhaust manifold, and this exhaust gas drives a compressor turbine, and it draws fresh air and actually runs in a boost condition to feed these cylinders so they don't have to draw air in through a vacuum, and makes it more efficient. After we take this power out of each of these systems and turn it into rotational power on the crankshaft, we come out, we'll bolt this engine to a generator or marine transmission, and from then to a propeller on a boat. On many of these engines you'll see, if you see tugboats on many of the larger rivers, the Mississippi or the Ohio, will have engines in them like this, and either 2 or 3 at a time.
Fluid power is very popular because it transfers power with very few losses. These brushes operate with fluid motors. Hydraulic oil moves through the motors, causing them to spin. The pressure to move the oil through the brushes comes from one pump. So little power is lost in the fluid, the pump can very efficiently transfer its power to all the brushes in the car wash. If the same thing was done with electric motors on each brush, it would be a much more costly and less efficient method. Fluid power. It determines how fast we move a fluid. Sometimes lives depend on how we control it. It's measured as the rate of doing fluid work. And sometimes controlling fluid power can help us control power in other systems. So we can try silly things like this.